So, the last speaker today is Ryan Budney from University of Victoria. I think he went to the first conference I organized in Rome, not here, but in the other university, at Sapienza, 16 years ago. So yes. It's the only survivor.
Yes, yeah, I've known Paulo for basically all my career. Yeah, thanks for having me. Everybody else here is new to me. I'm not really an applied topologist. I'm a geometric topologist that kind of dabbles in applied topology, and this is sort of accidental research with Thomas Kuczynski. He was visiting Victoria for a summer, and we would just sit around in his garden and chat, and this was something that popped out of our chats. Yeah, so let me, and I'm not even really going to talk much about persistent homology. I'm just going to be talking about sort of the geometry of filtrations, I suppose, and a special case where you can sort of see quite a lot of the geometry of the filtration using a little Morse theory in quotes. Morse theory itself, like classical Morse theory, it's a study of functions. Oh, look at that. Yeah, functions from a manifold to the real numbers, typically you have nice pictures like this, where here's the real numbers, and so your manifold in this picture is sitting in Euclidean space, and you're taking orthogonal projection onto an axis. Generally speaking, all Morse functions are obtained by, well, actually all functions are obtained by just embedding your manifold in some maybe high-dimensional Euclidean space and taking an orthogonal projection onto a real line. One definition of a Morse function is that it's defined by, you consider the derivative as a map from the derivative of a real value function as a map from the manifold to its cotangent bundle, so all the dual spaces of the manifold, and you demand that that map is transverse to the zero section. The reason why this is sometimes a preferred definition is this gives you an easy argument that Morse functions are open and dense in the whole space of maps, so that they're kind of generic in some sense. I'm just going to review some basic Morse theory. So the Morse lemma, it's one statement of it is that for a Morse function, if you're in a neighborhood of a critical point, you can find a little diffeomorphism between an open subset of Euclidean space in that neighborhood, such that in those coordinates, the function looks like its value at p plus a quadratic function, where m there is the dimension of the manifold. The coordinates are around p, so p of 0 is p, and those little epsilons are non-zero real numbers. So it just says that around a point that's not critical, the function just in coordinates looks like a linear function, not a non-zero linear function. So around a critical point, your function is sort of folding the manifold in some prescribed way. When you have a Morse function, either it's at a point it's either locally a submersion, looks like a linear function, or locally it folds like this quadratic function. And so in this case, you have a fold point here, a fold point here, here, and here, and everywhere else it is locally linear. So another way of talking about critical points is by looking at the Hessian. So the Hessian is the second derivative of a function. You can think of it as a symmetric bilinear function from two copies of the tangent space to the real numbers. And I should have said, so if you replace HFP with any symmetric bilinear function, Sylvester's law of inertia tells you this coordinate system, so that symmetric bilinear function, it looks like this quadratic function, where the coefficients of the quadratic function are these epsilon i's that can either be +1, -1, or 0. So it certainly applies to Hessians. So the subspace spanned by the vectors where the epsilons are 0, that's usually called the null space of the Hessian. Where the epsilons are positive, that sometimes it's called the positive eigenspace, and where the negative is called the negative eigenspace. So the triple that counts the dimensions of these, that's usually called the index of the Hessian, and that's That's up to change of coordinates. It's a unique invariant of the Hessian. So one equivalent definition of a Morse function is it's a smooth function, so that at all the critical points, the Hessian has zero nullity. Yeah. So one of the main theorems of Morse is that when you have a Morse function that when you go through a critical value, sorry, this is the easier theorem. If you go through a point that is not a critical value, so all the preimage points are regular, then the homotopy type of the preimage of an interval, it doesn't change as a passes, it goes through that point. So critical values of the function, this terminology is sometimes annoying. The critical values of a function don't actually have to be, so the critical values of a function means the image of the critical points it has. So the critical points are where the derivative doesn't have full rank. So the harder theorem of Morse is that if the pre-image of a point in the reals contains only one critical point, then the homotopy type, as you pass through A of these, the pre-image of these intervals, so A plus epsilon and A minus epsilon, it does change, and it changes by cell attachment. And you can kind of see that in this picture. So, for example, here's a critical point. The homotopy type of this, the preimage of this interval is an annulus, and below it is just a disk. Yeah. Okay. So that's sort of a pencil sketch of classical Morse theory. Now I want to talk about a couple variants of it. Yeah. So to get to talking about those variants, maybe some context. So Morse theory, you could view it as the starting point of what tends to be called singularity theory, and that people use that word pretty loosely, but the way I'm going to use it is the space of all maps from a manifold to the real numbers. That statement about Morse functions being generic, one way you can think of it is that this mapping space, it turns out to have a stratification where the codimension 0 stratum is the Morse function, and then you can ask, well, what's the higher stratification of it? Codimension 1 stratum are called Cerf cubic singularities. Let me talk a little bit about that. So what do I mean? So that's an infinite dimensional object. So what do I mean by codimension 1 strata? Well, if you have a map of an interval into that space that starts at a Morse function and ends at a Morse function, you can assume that map is Morse up to a small homotopy that fixes the endpoints. You can assume that map is Morse everywhere except at maybe finitely many points in the interval. And at those finitely many points in the interval, the function has this kind of cubic description where t is the time parameter of the interval, t0 is that degenerate point. I think I should have a picture of what this means, yes. So roughly speaking, what's going on is when t is below that critical value, you have, say, two Morse singularities, and as you pass through the critical value, they come crashing together and vanish. So these are called birth-death singularities, and if you keep track of the combinatorics, this might have index I and that index I plus 1. They're adjacent indices. One's always big. One's bigger than the other by 1. Canceling. If a lot of people here study topology, so you know about CW decomposition. So this is like the Whitehead theorem about how you can modify CW decompositions. You can sometimes eliminate lower dimensional cells with higher dimensional cells. This is sort of a Morse theoretic perspective on those Whitehead theorems about modifying CW decompositions. Okay. So that's one slight variant on Morse theory. Raoul Bott, he thought plain Morse theory was kind of silly because most functions that come up in geometry even though Morse functions are generic, oftentimes when you're dealing with something really geometric, especially symmetric, it's not a Morse function. So for example, take this height function on this standard linearly embedded torus. So there's a maximum circle, a minimum circle in red and purple down here. So think of it like a round torus sitting flat on a table. There's a maximum circle and a minimum circle. That's not a Morse function, but it has a lot of formal similarities to a Morse function. So a Bott-style Morse function is a function from a manifold to the real numbers. The critical point sets are manifolds, like submanifolds, and the Hessian, when you restrict it to the topological normal bundle, they have to have zero nullity. So that's what I mean by the Hessian when you restrict to the topological normal bundle. So that is, if you're careful, that is a well-defined object. Yeah. So this is the setup for Bott-style Morse theory. And so the Bott version of the Morse lemma, the cell attachment version, a Bott-style Morse function with a critical value A. Well, when you pass through that critical value, the pre-image of the intervals, it doesn't change by a cell attachment. It changes by attachment of a disk bundle over this manifold. Yeah. So for example, in this case, you've got a disk bundle over the circle and another disk bundle over the circle, and they're glued together. So it's sort of a boring annulus decomposition of the torus. Yeah. All right. So another example, which is maybe a little more playful, the real projective space. You think of that as the subspace of one-dimensional, the space of lines in a Euclidean space. Then the Bott-style Morse function on it is the one where you take the square of the angle between the line and a codimension 1 subspace. And that's a Bott-style Morse function. And if you think about it carefully, you're just attaching a single cell to the lower dimensional projective space. And so by induction, this gives you the standard minimal CW decomposition of real projective spaces. Okay, so this is a way in which these sort of the CW decompositions you like are often given to you by Bott-style Morse functions. Yeah. So now there's these things called two Morse functions. So and this is work due to Whitney originally, although he didn't write it up in quite this generality, but it was implicit in all his work. You take the space of functions from a manifold to the plane. There's a stratification of that, such that the codimension 0 stratum are the 2 Morse type, functions of 2 Morse type. So what I'll do, there is a description of this, like the original description of Morse functions in terms of transversality and all that nonsense, but it's sort of a higher transversality where usually you use the language of jet bundles or something like that. It's a bit of a pain, and every time someone talks about jet bundles, my brain blurs over and I fall asleep. So I'm just going to describe the local singularities, and they're familiar. So you could locally look like a submersion. So you go up to a coordinate, like local coordinates, taking local coordinates. So that's not a critical point. There could be a full singularity. So you're just on the first coordinate you remember, and then the remaining coordinates you've got a Morse type singularity. And then lastly, there's the cubic singularity where the time parameter is x1, the one that you remember over here. So it's that's a 2 Morse function. So these are generic and dense, all of that. So here is the Klein model sitting embedded in R4 with one of the standard projections to the plane, and you've got the sort of the full singularities are almost everywhere, and then there's these 2 cubic singularities where the full singularities come together and cancel. And then I have some decorations on it. These are the index, the analog of the index of Morse theory. I'll describe what that means. So the index of a full singularity, it's a triple. You've got a vector in the plane and 2 integers, I and j. So the vector has to be orthogonal to the tangent space of the full singularity. And then yeah, then what do? You look at the Hessian of, you take that function and you take the dot product with v, like project orthogonally into that direction, I guess is another way of saying it. And I1j has to be the index of that. So what are we saying? There's sort of I directions of the manifold that are folding into the vector v, and j directions that are folding the opposite direction to be folding in the minus v direction. I plus j plus 1 is the dimension of the manifold, and if you negate v, you switch I and j, and then otherwise this index is essentially well defined. Yeah, so that's the definition of an index, or at least that's the one we use. At two-Morse theory, there's not enough users of it for the terminology to be standard. This is just our own ad hoc terminology. If you like it, go ahead and use it. If you prefer something else, do that. This works for us and what we're doing. Yeah, so here's a ripple two-sphere in R3. So just take a like a soccer ball, football, sorry, and then you deflate it a little bit and kind of punch it so it folds over, and that's the picture, and then we're projecting into the grass. And yeah, so you've got this black has nothing to do with the fold singularities. It's just indicating the shape of the ball. But then there's the blue fold singularity, and then there's the red fold singularity, and there's the two cubics here. Yeah. Okay. And the indices are like that. You got the sheet folding over this way. So I'm suppressing the vector v because the vector is sort of drawn in plane. Yeah. All right. So that's the kind of thing that happens. Now I want to talk about not really persistent homology, but just bifiltrations of manifolds. So one thing you could consider is in the plane, take these quadrants. There's the point AB, and you take everything to the left and down, and then we look at so that you get a bifiltration of the manifold by taking preimages of these quadrants, and we want to see how the homotopy type. We want to know the homotopy type of that bifiltration. And when you have a two-Morse function, you can basically just sort of read it off. And some terminology we like to use, and again, there's not a ton of standard terminology out there for two-Morse functions. We're just making it up, whatever's convenient for us. And we try to make it consistent with traditions of Morse theory, but probably other people have other definitions. So a point is regular for the filtration. If in some neighborhood of that point in the plane, you have, whenever you have a map from one preimage of a quadrant to another, so whenever they sort of satisfy the poset relation, that induced map is a homotopy equivalence. So that would be one definition of regular. That's a fairly weak notion of regular. A stronger notion of regular that comes up is you could demand that those maps are not just homotopy equivalences, but they're the homotopy equivalences give you little commutative diagrams when you project down to the plane. So like fiber homotopy equivalences. And this comes up a lot, and this is a very useful way of manipulating these filtrations. So let's see, this theorem. Okay, so if you have a two-Morse function, provided your point in the plane is regular for f, and the boundary of that quadrant, so by boundary of the quadrant, I mean these two edges, provided those intersect the singular values of f transversely and without double points. So we're not allowing intersections like that. We're not allowing intersections like that where you have two of the singular curves where they cross each other and you're going through like that. Yeah. So those kinds of things are to be avoided. So we only want crossings like this, that, and so on. Then at that point, this is a fiber homotopy regular point, and the proof the proof is very intuitive. It's just like all the standard proofs in Morse theory. So, this is the statement of the theorem again. Yeah.
Before the proof, I just wanted to ask you about this. They're using regular in these two different ways, right? In the same statement, and you assume that it's quickly regular, and then you're proving that it's strongly regular. Is that what you're doing?
Yeah. So this is regular in the sense that there's no singular values at AB, and this is regular in the sense with the filtration. Yes. Yeah. Regular is overused. We maybe should have.
Now, is it three notions of regular or just two?
Well, in this statement, there's just two.
Right.
But yes, there's also where the maps are just homotopy equivalences, and then we just call that regular. Yeah. So
You're not using that.
Well, it's implied, but the fiber homotopy regular implies the other one. Yeah. So the important thing is the proof. So you've got in this regular case, you've got something like this, where the transverse intersections, and so you want to know what happens when you change A comma B. So here's your A comma B originally, and then say I'm going to move it a little bit to the right. You can consider moving it up later. If you move it a little bit to the right, so what I want to do is I'm going to construct a vector field on the manifold that flows this preimage to that preimage. And so how do I do it? Well, if you're on the red manifold, you make the vector field point to the right, let's say like a unit direction to the right, but then you have to force it to be tangent to the singular subset at the red points. And then you use a bump function argument to smoothly interpolate that to a right-pointing vector field along this black edge, and then you flesh it out to be. Then you can flesh out that whole vector field in the green neighborhood. We don't need it to be moving anything over here. So the vector field basically dies off as you move to the left end of this green brick here. And then now the point is that because of the shape of our singularities, these vector fields lift up to a vector field on the manifold. Right? The definition of the form of these fold points was that there are vectors upstairs that differentiate down to tangent vectors of the red curve. Right, that was at a fold point there was that x1 remaining, and so if you anyway, so that gives you these vector fields, and then you just lift the vector fields up to the manifold and flow, and they give you the diffeomorphisms that send the preimage of this quadrant to the preimage of the quadrant that's a little bit further to the right. So that's the rough idea of the fiber homotopy equivalence. Singular points for the filtration, you can have singular points of F. So we could have like a red curve running right through AB like that. We could have points AB where the quadrant is tangent to the singular curves, and you could also have cubic points running out. And so we have to deal with those as well. So you just sort of follow your nose and see what happens. So the case of the singular values of passing through and causing a tangency with the singular values, that's what you have to deal with. So you sort of imagine this case, you're shifting that to the right, and you pass through and create a tangency. So I could imagine that instead of like making my quadrant rigid like a square, I could just sort of poke the quadrant out a little bit, and by the previous argument, we're essentially doing the same thing by relaxing the condition on the quadrant and letting it be smooth. But now if I poke the quadrant out a little bit and push over that singular curve, well, what's going on? well, if you think about this 2 Morse function and you restrict it to that purple line there that I call C, the F restricted to that pre-image of C mapping to C, by the definition of a 2 Morse function, and this is a full singularity, this map is literally just a regular Morse function, thinking of C as an interval in the real numbers. So that's just a plain, boring Morse function. So all you're doing by poking out there is you're attaching a cell corresponding to the whichever index of the curve that's relevant. So it's not a dramatic change. It's just a simple cell attachment. The other case where the tangencies on the other side is a little bit more dramatic. So let's maybe think that through. So this case where the curve is largely on the inside and you pass through a tangency, that's a little bit different. And just like the previous argument, we could argue that this transition, it's what you get when you take this quadrant out here on the outside and you poke it in a little bit like that. Now if you think through what's going on, well, we are by undoing that poke in, right? We are basically just attaching this whole manifold that's over that purple square there. And well, what's going on is this function f, when you restrict it to that pre-image of that purple square, it is a Bott-style Morse function. It's a Bott-style Morse function from the point of view of projecting to the purple line direction. So what we're doing is we're attaching a disk bundle over an interval. Disk bundles over intervals are trivial, so it's a one higher dimensional, so it's really a disk across an interval that we're attaching. And it's sort of a relative attachment because on the top and bottom it's already there, it's already attached. So you're attaching a sort of a relative disk. And so it's a disk of one higher dimension. So those are the 2 main transitions that happen with 2 Morse functions. When you pass through one of these cubic points, if the cubic is entirely pointing out or entirely pointing in, you don't change the homotopy type of the pre-image of the quadrant. You do change its fiber homotopy type, but essentially what's going on is that you're attaching a cell and a canceling cell at the same time, or removing a cell and a canceling cell at the same time. So it's not terribly exciting. And then lastly, there's this case of you've got a double point in the singular set and you pass over it. This does change the fiber homotopy type, but the argument that if you remember the argument that if you forget one of the curves, you just have a nice transverse intersection, and the fiber homotopy type doesn't change. That argument, you use that same argument, but you do that argument for one curve, and you just don't define the vector field in the neighborhood of the pre-image of the other, and then you do the same vector field for the pre-image of the other, and you can stitch them together, and you get a vector field that flows this pre-image to that pre-image, but it doesn't preserve preserve fibers. So it's a similar kind of argument. It's kind of boring. It's kind of more complicated, but in not a very exciting way. Let's see. So a summary of what I just described. When you have a 2 Morse function, and consider the projections to the x and y axis on the singular set, and if the projections to those axes, the x coordinate as a function projected to the restricted to the singular set, if that is Morse, the projection to the y-axis restricted to the singular set, if that is Morse, ignoring the cubic points, then this bifiltration it has singular points consisting entirely of these outward and inward pointing tangent singular points, and these corner singular points where you pass through, I don't know what to call these, they're not exactly tangencies, but they're functionally equivalent to a tangent singular point in terms of how the homotopy type changes. And yeah, so passing through such singular points induces a cell attachment of the dimension, the index of the critical curve, provided it's outward, and the dimension plus 1, provided it's one of these inward ones. And so that's sort of the generic story. And then there's a lot to digest there. This is just sort of, when you see this, you just sort of, after you do it, after you see it, you just sort of work through some examples and think through the geometry. So for example, here we've got the punched football, and we've got the indices like this. So that theorem, it says, if you want to know how the homotopy type of the bifiltration changes, you basically only recall the curves that, when you walk along the curve, they're decreasing. So we kind of forget this part of the blue curve and this part of the blue curve. So, and then because these are, this is a, well, when you pass through here, this is a outward, an outward tangency. So you get this vertical line attached, and this is one of the, what are they called? These are the inward tangencies, and you get these vertical lines attached, but they're sort of, they create this sort of fishtail shape. And so that's how the homotopy type of the bifold, these curves I'm describing here are describing the transitions in the homotopy type of the bifiltration, and this is describing the dimension of the cell attachment. So these are 0 cell attachments. We used H because I think we preferred to talk about handles because everything was smooth. So one handle, 2 handle, 2 handle. And this 1 handle is canceled by that 2 handle later. So you've got this sort of funny situation where you go to 1 handle, a canceling 2 handle, and another canceling 2 handle. They both cancel that 1 handle. So the net effect is, if you go to here, you've got a genuine 2 handle, but you sort of created a lot of redundancy to get there. You created a 1 handle, you killed it, and then you added another 2 handle. And we kept track of the, what do you call it, Poincare on this as well. So this is just grabbed from our paper. But, so if you put it all together and think about the attaching maps, you can get the Poincare on this. So here's sort of a generic picture. So take a Morse function on a manifold and take the function from circle across manifold to R2, where you're basically putting that Morse function into like polar coordinates. Right? So the critical values of your Morse function become critical circles for this 2 Morse function. And when you look at the homotopy type of the bifiltration, you get essentially a duplicate of what happened in the previous case. These rounded curves, they go off to infinity. You chuck the increasing parts away, and you get these fishtails over here. And the cell attachments are almost the same as in the previous case, where you've got an I cell and I+1 that cancels it. So, Klein-Bottle example is maybe more exciting. There's a lot going on. Again, you only keep track of the decreasing curves. The increasing curves you chuck, and you've got this phenomenon of when you transition through, is it an inward or outward tangency, and it sort of tells you whether or not you get these fishtails or these sort of just rounded curves. Yeah. So that's the basic idea. The Morse theory we're talking about here, so this originally goes back to Morse in the 30s. Bott's work was in the 50s. I didn't know Bott. I knew one of his very first grad students. So Bott, his first grad students were all electrical engineers. And there's a prof at Cornell, Dave Delchamps. He was, I think, Bott's second grad student or something like that. we played hockey together in the Ithaca City League, and one day our team got into a what's called, the Italians maybe don't understand this, it's called a bench clearing brawl, where everybody takes off their gloves and starts punching each other in the face. And so Dave was on the other team, and our team was, they were beating each other up. Our goaltender broke his femur. He had to go to the hospital. It causes a lot of bleeding. Yeah, but Dave and I, we saw there was the chaos, and we walked over to the side, and we sat on the bench, and we just started talking about Morse. Yes, and so Whitney, much of singularity theory of manifolds was developed by Whitney, although Whitney came from a different school of mathematics where he didn't do things in maximal generality. He just did nice examples. So two-Morse theory was essentially set up by Whitney, although you don't get, you read his papers and you don't get clean citable theorems, but you just see the techniques, and most people just duplicated the techniques. And then I think the first clean write-up was by Mather in the 70s. So our paper came out, I guess, a year ago, and shortly after our paper came up, there's this Asif and Baryshnikov preprint that popped up. It does sort of similar things, but I don't know them, so I'm not going to comment on their paper too much, but there's a lot of this is trivial, that is trivial in their paper, and I guess depending on your perspective, maybe it is. But so that's the basic idea of bifiltrations. So it's sort of generic bifiltrations in the sense of using functions to the plane, smooth functions to the plane for manifolds. I suppose I should say what motivated this paper. Thomas and I think we had gone to a bunch of bi-graded persistent homology conferences, and I suppose we got a dour, sulky perspective from the people there. They're saying it's too hard to compute. It's what is there's sort of a wild representation theory is I think the terminology, and Thomas and I both thought, well, it's not so bad. Like maybe from a very from certain algebraic perspectives it sounds complicated, but the underlying geometry I think is it's fairly easy to transition from. If you know, so, but this does demand a lot of, do you know all the critical values of your function, and have you computed all the Hessians? I think finding the critical values of a function is a computationally intensive thing. If you're dealing with polynomials, I guess Italy has a lot of algebraic geometers that can tell you how to do it as quickly as possible, I imagine. It's not easy. It's not like super easy, but it is. There are standard algorithms to do these things. And oftentimes, if your functions are, if they come up in some geometrically relevant context, it's just transparent what the transitions are, what the critical values are. So this is mostly a counterpoint to. So I interact a lot with Mike Lesnick and Peter Bubenik, and I just there's a lot of terminology, but talking about how complicated this is, and. In some sense, there's complications, sure, but I think these examples are meant to indicate that at least in a big family of examples, there's some very nice geometry underlying what's going on, and the way the homotopy type of these bifiltrations change is not radical. I guess another theme that comes up in the form of these arguments, originally when we were writing the paper, we were using these quadrants. But then, as when we did the very first proof that the homotopy type, it doesn't change in these transverse situations. That argument we're giving, it basically also tells you that if you change the quadrant by a little diffeomorphism, the homotopy type is not going to change. So we didn't really need to use quadrants here. You could use a poset of smooth submanifolds of the plane. So if you're like a sheepy person, there's probably some nice terminology for what you have to talk about one-parameter families that are smooth one-parameter families. But yeah, we didn't really need to use quadrants for any of this. You could talk about posets of submanifolds as well, coming from Morse 2 functions. Okay. So that's it.
Yeah, it's like, have you really made explicit?
What?
I don't know if that's a well.
I guess it depends. It depends on exactly what you want to get out of this. This is basically just sort of a high-level picture of how you can read off persistent modules, provided you know basically everything there is to know about this smooth function. So it's I think for me the main point was other than knowing the singular values of the function, there's not really anything standing in your way to computing the persistent homology. It's just a
But just give you any hints about how you would maybe think of something, like think of ways to describe these multi-parameter modules.
Well, I suppose it also really depends on the multi-parameter modules. How are you coming up with them? So our motivation came from Thomas's work, where he did have some multi-parameter modules, and he was noticing some trends in his computations, and he wanted to be able to say the things that I'm seeing in my examples should be all that happens, and so this basically says that his examples were generic. He basically was describing everything that could happen, but he was just working from examples in quite applied context. Most bifiltrations that people come up with are probably not preimages of subsets of the plane. Oftentimes bifiltrations probably don't come up that way. So I don't know. The utility of this is more just the two filtrations that come up from two Morse functions are really completely analogous to the one filtrations from regular Morse functions. That's what I get out of it.
Maybe this was implicit in your talk, or explicit and I missed it, but one of the nice applications about the one-dimensional version in the case of manifolds of 2 dimensions is to get a pair-pan decomposition. I'm wondering if one could use this techniques in low-dimensional manifolds to get nice decompositions.
Well, this is quite analogous to if instead of using quadrants, you used instead of dividing the plane into 4 and taking one quadrant, you can divide it into 3, and then that's a very popular thing in 4-manifold theory now. That's called 4-manifold trisections, and so this is very closely related to that. So the theory for doing a trisection version of this is going to be identical. So that's something that people do. Trisections of 3 manifolds are maybe not quite as interesting, but I guess trisections of 3 manifolds are more or less like Hagar decompositions, and So this is related to some standard decompositions. I'm not. I mean, these are the ones that come to mind.
So I wanted to ask you. So you said that there is a generalization to function into Rn, say.
Yeah. So one of the problems when you want to do this with maps to say arbitrary manifolds or to Rn is that you kind of have some freedom in choosing which singularity theory you want to work with, and some singularity theories are easier to work with than others. Some are more finitary in nature, and some they depend on they become in highly parametric versions where you talk about smooth structures and things like that. But so you can even do this in like a PL context for PL maps, but then you also lose sort of a finitariness, right? The nice thing about two Morse functions is you just have these, you just have a finite number of indices that are possible. But with PL maps, you get monkey saddles and things. And similarly, you talk about singularity theory for maps to, probably it starts getting weird around R6, R7. You have sort of a very wide array of possible singularity types, depending on exactly which singularity theory you work with. And the answer is going to be completely analogous, but the description is just going to get more and more clunky. I don't know a convenient singularity theory that packages it all together nicely without an enormous amount of burdensome language, but maybe that's just my own fault for not knowing enough singularity theory. Yeah, but it's all stuff that can be done. It's just a question of writing it down in a way that's useful to you. And I personally don't have any guidance for what do I want the theory to, what do I need the theory to look like. I don't have an application in mind where it's telling me I need the theory to look like this. So that would guide me on which singularity theory to choose. Yeah.
And is there a discrete analog, like there are discrete Morse functions?
Well, I mean, I guess I view discrete Morse theory as sort of like a highly refined version of the PL Morse theory. So I think there is a discrete version of this. Actually, my co-author might have already written it up. But I don't know if it does everything you might want it to do. Discrete Morse theory has some nice features, and so exactly how much it is an analog kind of depends on what you want to get out of it, I guess. I think Thomas does have some discrete version of this. I don't know if it is quite as great as classical discrete, like Foreman discrete Morse theory.
Another question? Let's thank Brian again.